And remember that what we did is we had solutions for an for flow into a cylinder for different dimensionless radii and different dimensionless times. We could use the Bessel function equation, which we're not going to use. We'll use the approximate equations by Edwardson, which are only applicable for infinite acting flow, or there's some plots, or there's some tables, and really any of those is fine if it's infinite acting flow. If it's not infinite acting flow, you can't use the Edwardson at all ones. But the biggest challenge with this is that those solutions were only valid for a constant pressure in the reservoir, when in reality the pressure declines with time. You produce fluids and pressure drops. The decline is probably going to look something like this smooth curve I have over there, but we're going to cheat a little bit and we're going to approximate this by having step changes. So even though the pressure won't be constant, it will be constant for a period of time. So it'll be constant for this period of time, and then this period of time, and then this period of time, where the pressures are given over here. So we'll need these delta P's. And delta P1 is 1/2 Pi, that's the initial pressure, minus P1. So what you would be given is a table of time versus pressure, right? So reservoir pressure, that's going to come from probably pressure gauges in your wells. Delta P2 is 1/2 times the initial pressure times your pressure at the second time step. Delta P3, well, the pattern changes a little bit. It's 1/2 P1 minus P3. And then finally, in general, delta Pj, for any j that's greater than 3, or really greater than or equal to 3, is P of j minus 2 minus P of j. Okay, so you need to calculate those pressure drops. And then what we learned last time is that we utilize the principle of superposition. What does that mean? It means that we add solutions on top of each other. So it's effectively like you have a bunch of individual solutions and you're adding them up, you're summing them up. That's why we have the summation. So U is a constant of the aquifer we can calculate. J is equal to 1 all the way to N. N is the final time step. If you want to calculate the cumulative amount of water influx, WE, at a time N, you sum up over N, where you have delta PJs, where again delta P1, delta P2, delta P3 are given, and then times WED. And this isn't a multiplication, this is WD of that dimensionless time. So it's TD at the final time minus TD at the J minus 1. And this is the common mistake, that someone might try to do TDJ minus TDJ minus 1, but that's not right. You have to do TD of N, the time that you're the final time you're interested in, minus TD of J minus 1. And then a good way to solve this is to set up a table. So you're given time and pressure. So T is equal to 0, your initial pressure. T1, you have P1, etc. You can calculate your delta PJs using the formula we had before. Calculate your delta T. Now this is what's complicated. This is I wouldn't call it complicated, but it's an easy place to make a mistake. It is going to be the final time, Tn, minus Tj minus 1. So Tn minus 0 is Tn. And then here you have Tn minus T1, Tn minus T2. And those are times in hours, right? Because T was in hours. You can put it in dimensionless time using our equation for dimensionless time. So you just take this number and multiply it by this coefficient. Now that you've got these delta TD, these dimensionless times, you can evaluate WED for each of those times. And you can do that, again, using the tables, the plots, the equations. If it's not infinite acting flow, remember infinite acting flow basically means early times, or if the aquifer radius is a whole lot bigger than the reservoir radius, it's sort of, then you could use the infinite acting tables, but otherwise you'll have to use the non-infinite acting solution. and you get your WEDs here, and then you do the summation. So you add up each of these WEDs times the delta P's. So you sum that up and you get the WE. Okay. Now, one thing I'll state about this is that this is only for one final time. If you want to figure out the total cumulative influx after a certain number of hours, you can do that. You have to redo this exercise for all later times. Okay, and I'm going to go to talk more about our example we did last time, but first off, I'm going to look to see if there's any questions this spreadsheet or parts of the spreadsheet with you, so that you can do it yourself later if you'd like. But let's look at the data. This was data that I shared last time. This is the date. Okay, this is an old reservoir that started producing in 1964, and this was the time in hours. So this was, the dates were converted to time. So T is equal to 0, and then you went to 188,000 hours. This is the reservoir pressure that we measured with pressure gauges. This is the oil, gas, and water produced. I don't think we're going to need that right now, but I think we might later. And these are the formation volume factors of the oil at those pressures. What we really need is these two columns here. Okay, and what we might want to do is we want to calculate the cumulative amount of water influx that came in. Now, a common question might be, why do I care? Right? So why do I care how much water came in before? Okay, so obviously it's not 1985 anymore, but let's pretend like this, we had data up until today. Okay, this is just an old reservoir, but let's say it's a current reservoir, and we got data up till January of 2021. Well, you would want to know how much water was encroached so that you had a good idea of what the new saturation of the reservoir is, and you could use it to predict how much water would be encroached in the future, and that would help you to make some decisions. So having knowledge of the past helps you make decisions for the future. And that's our job as reservoir engineers, is to make decisions for the future. There are some other properties that I went through last time. They're all given here. Okay, and then what I did is I made some initial calculations. So I calculated F, for example, which is the ratio of the angle divided by 360, and so it's a full circle, so it's 1. The area of the reservoir, which came from the bulk volume, effective radius. We've done all this, so I think I'll go through this quickly. We calculated this, this U constant, and what we did last time is I asked you to calculate the amount of water encroached in January 1965. So really after 87, 84 hours. And if I go to here, I'm going to go to this tab J is equal to 2. And don't worry, I'm going to post the data for this spreadsheet. And I'm going to talk more about that in just a moment. So here is a table that I created. Okay. And you notice in this table, I don't have any data after 87, 84 because that's not what we were asked right now. We were only asked to figure out the total water that was encroached after 87, 84 hours. And at that time, the pressure was 2496. So I calculated my delta PJs, so delta P1 and delta P2, which were the average of 2532 minus 2503, and then the average of, 2503 minus 2532 minus 2496 divided by 2 is 18. I calculated the delta T, and this is where it's easy to make a mistake. This delta T is the final time, 87, 84, minus the initial time, which is 0, so it's 87, 84, and this is 87, 84 minus 65, 6, that's 2208. I have an equation in here, so I converted that to dimensionless time, so 87, 84 times those constants. I have a column here which maybe I should have calculated, but it's the ratio of the dimensionless time divided by the dimensionless radius squared. That gives me an idea of whether or not it's infinite acting flow or not. It is actually in this problem, and I think I told you that was the case. So maybe that was one of the reasons why I didn't even bother to calculate it, although it's always a good idea to do so if you know what RED is. And then we can calculate WED at these dimensionless times. Okay, it's infinite acting flow, so I don't need to worry about the dimensionless radius. I could use the plot, the Edwards-Hint et al. Equations, or the tables. We did all three on Friday. We did all three and we got similar results, and we should have. They're really all the same thing. And delta T is less than 200, so I think that this is the correct WED. We may have gotten slightly different numbers using the plots of the tables, but they were all within 1 or 2% of each other, so it's all good. So we take this WED, which is right here, 39.8 and 10.75. We multiply it by the delta P, so we multiply this by 14.5. We multiply the 10.75 times 18, and we get this, these right over here, and we added those up, and we multiplied it by B40, which is the U term. That's the U term over here. Calculated down here. So U is calculated as 14.68. So I multiplied it by the sum of 449 and 193, and I got 909,000 barrels. I think I said on Friday that I had 918,000 barrels. That's why I ended it. The difference there is probably whether I use the equations or the tables or the plots. But you know, a couple significant figures is probably sufficient. So even to say 910 or 900,000 reservoir barrels, we're looking for close to the right answer. So a little over 900,000 reservoir barrels is how much water was encroached into the reservoir with time. At that time, 84 hours. Now, that only tells me how much water came in at that time. If I wanted to calculate what it is at less time, 6576, and greater times, I have to redo that calculation all over again. And if you go to the late times, like all the way to 188,448 hours, that's even more tedious. So the Van Everdingen-Hurst model is very accurate. It is tedious. And so I did this on a spreadsheet. An alternative way to do this, and a good one, would be to maybe write a Python code to do that, right? So if you wrote a Python code, you could make it general and it would work for any problem. You just put in some inputs and you give it the data and it could do that. And so that would have been a great homework assignment to have you write a Python code. I think, I haven't decided for sure yet, but I'll probably not make you do that. But that would be a really neat thing to do. And it would be very general and fast and all that. One of the complications with the Python code is it's very difficult to use the tables and the plots in a code because you got to go look those up and do that. Now I think with in 2021 we've got such sophisticated tools that I bet that there's definitely ways where you go to a table and do an interpolation over there. Probably ways to do it in a plot as well. But we do have the equations and the models, and you might even use the Bessel function solution if you were ambitious with that. I am not going to go through all these other times. But about a year or two ago, I made a video of this example problem, and it is in your document. So I'm going to post that Excel spreadsheet, or at least a skeleton of it with the data. And if you go to this link right over here, I go in detail about that example problem and another example problem as well. So I highly recommend you watch this, especially before doing homework number 3, because I think that homework number 3 will be very similar. But long story short, when we solve that, what we get is at these different times, we get the amount of water encroached with time. And you could plot that up so you could see how much cumulative water comes up with time. So You can see here in January 1965, I got 909,000 barrels. That was my solution here. If I were to repeat that for all these other times, you could see what those solutions are in this column. The VEH method is very accurate. It's the most accurate, okay, but it's tedious. Okay? And it's tedious because I have to redo the whole calculation from scratch for each of the individual times. And in that Excel problem, I only had 9 times, but what if I had 90 data points? Then I'd have to redo it. Now, maybe if I wrote a Python code that, and I wrote it once, then I just input the data and it does it. So that would be okay, but that code might take a little, while to run. And in fairness, some of these models were developed decades ago where we didn't have the computational power that we did today. But I'll also say that even with the computation power we have and everything like that, I, as an engineer, always like to calculate things more than one way. And I usually like to do things the simple way at first to kind of get what we as engineers call back-of-the-envelope calculations, and then I like to verify it with the more complicated ones. So what I'm going to teach you next is the Fetkovich method. It's called the Fetkovich pseudo-steady state method. And what's nice about this method is it's almost as accurate as a VEH method and a lot simpler and less tedious to compute. Okay, so it's almost as accurate but a lot simpler. Okay. Now the math to get to the final solution isn't all that simple, and so we'll spend at least the rest of today going through that. But once you have the final equation, it's fairly easy to implement, or at least it's fast to implement. So what we have is, recall that WE, we'll say that we'll call this WE is equal to WI CF plus CW. That's the formation and water compressibility. Remember, WI is the amount of water in the aquifer, times PI, that's the initial pressure, minus the average aquifer pressure. Remember, this was sort of the small pot aquifer. And it tells me how much, if I waited long enough, if I waited well, theoretically infinite amount of time, but a really long time, this is how much water would encroach. Okay, if we wanted it less times, then this might not be accurate. Okay. I can also write this as WEI times 1 minus PA bar divided by PI, where WEI is CT, which is CF plus CW, times WI times the initial pressure. Okay, so if you don't quite see where that goes to, then just multiply it out. Multiply it out and show that these two things are the same, right? They should be. So this is WE. This is the cumulative amount of water you would do at long times. If we were to differentiate this equation, so dWE dt, all right, well, WEI is a constant and PI is a constant, but PA bar is going to change with time. If you take the derivative of that, you get minus WEI over PI times dPA bar dt. Okay, so this comes from differentiating this equation with time. and PA bar is the only thing that changes with time. Now, what Fetkovich said is he proposed that the water influx rate, QW, which is the change in the cumulative rate with respect to time, so that's barrels per day, is equal to some constant J times the average aquifer pressure minus the reservoir pressure. So I should say, we got a lot of different P's here. So I'm going to say this PI is the initial pressure. It'll be the same for our purposes in the reservoir and the aquifer. PA bar is an average aquifer pressure. Say average because it might vary over the aquifer, but we'll average it up and give it one value. And then this P here is the reservoir pressure. Now this equation should sort of look familiar to you, especially since you just had a quiz on Friday and had to watch my Reservoir 1 video. This equation we used for pseudo steady state flow from a reservoir into a wellbore. Okay, and so it's completely analogous. So this is the water influx rate from the aquifer into a reservoir. It's proportional to a drawdown pressure, the difference between the aquifer pressure and the reservoir pressure. Okay, and J is that constant. And I'll show you what that constant is, but we learned what that constant is in a reservoir, and it's very analogous, and I'll show you that equation a little bit. So now we have this equation for dWe dt, and we got this equation for dWe dt, so we can equate them. So then, minus WEI PI dPA dt is equal to J times PA bar minus P. Okay, so WEI is a constant, right? It's CT times WEI times initial pressure. PI is a constant. J is a constant. P might change with time, but we'll leave that right there for now. But we got this dPA dt and PA bar. So we'll ignore any change right there with the pressure. But what you have is dPA dt is equal to this. And so this is an ordinary differential equation, an ODE. And we will, and we have an initial condition, which is PA bar is equal to PI or something. And we have to solve this ODE. Now, this isn't a particularly hard ODE to solve. It can be solved with separation of variables. So I'll probably want to bring my delta t over here, and I want to pull all this and bring it over here. And when I do that, what you have is the integral from the initial pressure to the current average aquifer pressure of 1 over PA bar minus P dPA bar is equal to the integral from 0 to t dt. And I should have put this in front, but I'll multiply that by the J PI WEI. All right? So this is extremely easy to integrate. So the integral of 0 to t of 1 dt is just t, right? So the right-hand side is super simple. The left is not too complicated. It's the integral of 1 over, think of it as 1 over x, or 1 over x minus 4, right? How do you do that? Well, that's the natural log, right? So this side is ln of PA bar minus P over PA bar minus PI. That's that integral. So the integral of 1 over x is ln of x. So from PI to PA bar. And again, the right-hand side is super simple. It's JPI over WEI times T. Got that. And then what I want to do is solve for PA bar. Oh, I'm sorry, I had a little mistake here. This is PI minus P. All right, and PA bar minus P over PI minus P is equal to that. You're going to take the exponential of both sides. So e to the ln gets rid of that ln, so you have PA bar minus P over PI minus P is exponential of minus J PI WEI of T. Okay, and then I'll solve for PA bar. So PA bar of T is going to equal to, no, I'm going to say PI bar minus P. I just leave the numerator there. Is equal to PI minus P e to the minus J PI over WIT. Okay, so that was a little bit of math. I might have gone through that a little fast, so if you need to, then after class, when the video gets posted, go back and pause the video, maybe try to work it out yourself and see that you get the same answer. I have these equations on the PowerPoint slides as well. But we're still not done yet, so that was hard enough, but what we have is we've got this equation right here. And then we're going to go back to this equation. Okay, so remember this equation, which says that the dWe dt is equal to J times PA bar minus P. Well, now we have an equation for PA bar minus P. So we can substitute this in for this. And so it'll be a new differential equation in terms of time. So let me do that now. So dWe dt is equal to J times PA bar minus P. So I didn't write anything new there. But now when I do that substitution, I get J times PI minus P times e to the minus J PI over WEI times T. Okay. So now we got a new differential equation. dWe dt is equal to that, and I got a time in there. Okay. So I want to solve for WE. So solve this ODE for WE of T. That looks harder than it is, I think. Okay. This is a constant. Okay, we're going to treat that as a constant, at least for now. This is a constant. So you've got like a constant times e to the minus something t. Okay, what is the integral of e to the x? Integral of e to the x is e to the x, right? What's the integral of e to the 4x? Well, it's 1/4 e to the 4x. That's all that this is. This is dWe dt, which you want to integrate, and you got e to the, minus something t. So it's like e to the, e to the 4x or e to the minus 4x. So that's relatively easy to integrate, and when you get that, you get WET is equal to WEI, that's this, divided by PI times PI minus P times 1 minus e to the minus J PI WEIT. Okay, so this tells us how much water has come in if the reservoir pressure is P. Okay, so that was again a lot of math. We took some derivatives, we did a couple of integrals, we tried to integrate these ODEs. But now we have a solution for WET, and maybe you want to go back after class and try to rewatch that video, work it out yourself, see if you can get that. We do have a similar problem that we had in the Van Everdingen-Hurst problem, and that issue was that this reservoir pressure P is not constant. It is changing with time, and again we could kind of do some sort of approximation where we assume that the reservoir pressure is constant for a period of time and then drops. So what we're going to do here is say that over a period of time, the change in WE from the last time, so how much additional water was encroached, is going to be WEN is equal to WEI over PI times PAN minus 1 bar minus PN bar times 1 minus E to the minus J PI WEI delta T N. Okay, let me explain this for a moment. You should see some similarities between these two. Okay, what this was, the one I have boxed, that equation would say if I were to drop the reservoir pressure from PI to P, and it were to stay at P for a really long time, then this would be the amount of water I would encroach at the end of that time. That's what that is. Here, what I'm saying is that, well, that's not quite how the reservoir pressure drops, and I'm going to approximate it by being a constant pressure for a certain amount of period of time. And so what I've done is I've done this delta WE instead of WDN, which tells me how much additional water has encroached in the last time step during delta T. So you see a lot of similarities here, except that we're not going to use the initial pressure anymore. Instead, we'll use the average aquifer pressure at the last time step minus the reservoir pressure at the current time step. That's what the subscript N means. Most of this is the same in brackets, except I'm not using the total time anymore. I'm using delta T N. So it's the current time minus the final time. And one more thing to complicate things is that this delta T is actually the change in time from the last time step to the current time step. Okay, so we're going to do this, and I'm just going to finish this up by saying Pn bar, that's this thing right here, is equal to 1/2 Pn minus 1 minus plus Pn, so it's an average. So you know, we use bar a lot of times to indicate average, so it's an average of the last pressure of the reservoir, the last time step and the current time step. And then PA N minus 1, that's this thing, is equal to PI times 1 minus WEN over WEI. Okay. And then everything else you get in there. So don't worry, we're going to do an example problem on this. In fact, if you want to learn more, you can just watch that video that I mentioned on aquifers. So in addition to one on the VEH method, I actually do the same problem using the Fetkovich method, but we'll do that example too in class. So you know, maybe we'll do that on Friday. But I'm going to review all this on Wednesday because it is complicated and there are a lot of equations, and then we might need to see it in more than one way.